more than aggregation. It's sedimentation as well. And as you'll see before the day's over, sedimentation involves quite a lot of other factors. In a stirred tank reactor, a cylindrical tank with stators in it and then strakes on a rotor that rotate past the stators, commonly used in water treatment. The assumptions like that might be reasonably valid. That is, particles collide and form aggregates and settle out on the bottom if it isn't a continuous flow through. But even there, the problem is compounded by the fact that the velocity gradients range from very high velocity gradients at the edges of the strakes and rakes and stators, and very low at the wall. So you don't have a uniform velocity gradient. You have aggregates being broken up in the high velocity gradients and reformed and perhaps very slowly out near the wall. It's a complex situation. There are quite a lot of papers written on it, and while I'm tempted to just give you a lot of papers, I'm afraid that you'd spend an awful lot of time on it without that much benefit. So I thought I'd just sort of summarize these things for you. Last hour we began to talk about deposition of sediments.
The number concentration for this problem probably is too high. I made a note here. The solid volume would be greater than 1 cubic centimeters.
10 to the 13th per cubic centimeter?
Yeah. I don't know.
10 to the 13th?
Yeah.
Greater than 1 cubic centimeter?
Yeah, according to the number of particles and the diameter of the
You
particle.
can't have that number of particles that size, is that what you're saying?
Yeah, I think probably this number is too large. Or
The diameter is too large?
Or maybe we can use another diameter, a smaller.
Greater than 1 per cubic centimeter?
Yeah.
Or greater than 1 cubic centimeter of particles? Oh my.
So the solid fraction would be greater than
Yeah.
1.
Actually, you have 5 cubic centimeters.
Yeah.
Yeah, it's almost solid
it's
particles. Huh?
Impossible. Yeah.
Yeah.
More than that.
Oh.
Yeah.
Yeah. Yeah. Choose some other particle size. Just choose some other particle size.
Okay. Smaller.
There. And whatever you did, I'll accept it. As long as you got the relations right.
One more question. There seems to be a discrepancy in the formula for the rate of particle removal, the Brownian motion. It shows up as 2/3 in the notes.
Yeah, the
class.
notes say 4/3. Boy, I don't know how that crept in.
So it should be
Somewhere in there you divide by 2. When you have 2 particles colliding, then you want to count that as one aggregation. So you divide by 2.
So it should be 2/3? No, 4/3.
The book says 4/3. Now, I'm pretty sure that's right, but I'll have to go back through the whole computation and check it, or find some other reference. So, and I'll find that out for you. It's very likely 4/3.
Okay. Well, maybe I'll check it.
I can't tell you on my feet.
Okay, that's fine.
Back in there somewhere where you divide by 2. Okay, so if you have problems with that first problem, use a half a micron particle if it gives you any problem. In any case, you'll get full credit for it. Okay, last hour we were talking about sedimentation, deposition, and the first part was settling velocities. And I listed Stokes relation. Which assumed that the inertial forces were negligible. That is, that the water flowed around a settling particle with just viscous resistance to flow. And that the settling velocity was constant. Those are Stokes assumptions. And then we talked about the Richardson-Zaki equation. For hindered settling, which was W sub H equals W sub S, 1 minus the volume fraction, to some power, and I said most people take it to be 5. There's another relation that's important, and that is when you have a, well, I should say, first of all, this is for discrete aggregates. That is, each aggregate retains its identity as it settles down through the particle. When the particles all touch one another, or that is, when the concentration is high and the particles can all form some kind of an open network, then the particles will, it might be some very unstructured network of particles. Then the particles may not settle because the settling velocity of the individual particles is quite low. So that hindered settling, which depends on the settling velocity of the individual particles, isn't very effective. And when that happens, what you see is a function of time, let's say log time, against log H for settling in a cylinder. If we call this H, you see that nothing happens for quite a time, and then it falls off in a log-log fashion. And the curious thing is that if you make the initial suspension depth greater, then what you'll see is that it will take a longer time, and then it will fall off at about the same rate. This is purely empirical. So you have a log-log relation. What seems to be happening is that the unstructured material, slurry, rearranges itself under the gravity forces and thermal motions of the particles until there are local aggregates. That is, until they're with pores between them. Then at that time it begins to settle, and it settles in a kind of a consolidation arrangement. The reason I describe this is that in slurries, for example, material dredged by a dredge and pumped through a pipe so that at high velocity, so that any kind of aggregate structure is broken up. We'll call it a slurry. It takes a while for the aggregates to form regions of greater density and lesser density that water can get through. Then it reverts to this kind of a system. What I'd like to emphasize here is that the structure the way the particles are put together determines its behavior. We'll come back to this at a later time. Its practical application has to do with settling ponds for dredged material, where material is pumped into a pond and allowed to settle or consolidate with time. Well, so far what I've described is sedimentation in cylinders, just static sedimentation. You stir it up and let it settle. It's useful because it gives you some information on how the material behaves without velocity gradients and without shear stress on the bottom. But in order to study the deposition in real systems where the water is flowing, it's necessary to observe deposition from flowing water. And that's done in two ways, one in the field and one in the laboratory. The laboratory one is the one I'll discuss now because it occurs under conditions that are more or less, well, I should say, pretty well controlled. We use a flume, a channel, that just a rectangular channel, and I'll describe several of them before I'm through. It looks like this with some kind of a pump arrangement. And a return line, or lines. The one I'll describe had two lines in it. The pump with a variable speed motor drives the water or suspension upstream where it comes up and flows back downstream in the flume. So the water is flowing downstream in the flume in this direction. The slopes are made adjustable so that you can change the velocity of flow, and the motor speed is also adjustable so that the discharge Q up the channel can be regulated. Flumes are, for the purposes I'm going to describe, are designed so that the shear stress on the bed, tau sub W, is just a little bit smaller than for deposition studies than the shear stress in the return line. The reason for that is that you want to keep the material from depositing in the return line, but you want the velocity gradients to be as close to those in the channel as you can get because of aggregation processes, that is a breakup. And you want to minimize the breakup here relative to that in the channel itself. So we have a device where we can change the slope and the velocity of the flow. We can also, of course, adjust the depth. They range in size from about 30 typical hydraulic lab flumes, from about 35 feet, say, to, I had one 1,000 feet long. But most the 1,000-foot one didn't have adjustable slope. But most of them are on the order of 60 to 100 feet. And most of the studies I'll describe here used 100-foot long flume, 3 feet wide, 100 feet long, and the depth was on the order of a foot. If you ever do a flume study, it's important to keep the depth small relative to the width so as to minimize the effect of the sidewalls on the flow. What you'd really like to have is just a two-dimensional flow where only the bed affects the velocity profile. And by keeping the depth small, you can do that. The 1 foot depth was a compromise between needs to measure and depth. So we had the method of operating this for deposition studies is to fill the flume with salt water so that you have cohesive particles, then bring in a sediment and add it to the flowing water, or if you've just done if you have all the material deposited, increase the velocity to some high level, say 3 feet per second in the channel, and stir it all up so that the material is all in suspension. Then reduce the velocity to one such that the material will begin to settle, deposit on the bed, and let it stay at that one velocity for a long time and observe the rate of deposition. Now you all see the experimental conditions, pretty straightforward conditions. The flume differs from, that is, the conditions in the flume differ from those in an open channel in an estuary, because the material has to go through the pump and up through the return line. Then it's completely mixed at the upper end, vertically mixed. But during its travel down the channel, if it develops some kind of a vertical profile, it will do it as it progresses along the channel. So you don't really have an infinitely long channel, although your first impression might be that. Then whatever processes that occur in the channel are changed by its return through the return system. The reason that it's useful, one of the reasons that it's useful for our studies, is that it turns out that the concentration profile is virtually, the concentration is virtually constant throughout the profile. Remember, we had a relation last quarter that said the concentration at any depth, y, let's say, relative to that at any other depth, a, is equal to d minus y over y times a over d minus a to the settling velocity divided by 0.4 u star. Remember this? And that for gravels produced a concentration profile y that looked like this for coarse material. So that is, the upward diffusion at equilibrium compensated the concentration gradient so that at equilibrium this occurred. But for very fine material, let's see, it went something like this. For very fine material, it was something like that. In our case, the settling velocities are so low that we have this kind of a situation. Concentrations virtually constant from top to bottom in the flume. Now that's not true in every case in estuaries, and I'll describe circumstances where that isn't true when we get into dealing with estuarial systems. But because the concentration profile is virtually constant, this is reasonably representative of flow in an open channel. The simplest way to begin describing to describe what happens is to refer to some experiment. And if you'll turn to page Figure 13, page 42. You'll see some concentration versus time plots. Note that the ordinate is the logarithmic scale and the abscissa is time. And that after some initial curvature, the lines are practically straight. So that we can write the concentration, the rate of change of concentration, or the concentration as a function of time, is an exponential, decreases exponentially. This kind of condition means that a fraction of the material was deposited per unit time, right? We're talking about an exponential decrease. So we can say dc dt is proportional to minus c. I'll call it kc. For that portion of the period where it's low. There's two things that we need to consider. One is the flux to the bed. That is how fast the material is going to the bed. And that flux is equal to W sub S C, right? This is, let's say, centimeters per second, and this is grams per centimeter cubed. And that's grams per centimeter squared per second of flux downward. In this flowing water, however, the particles that go to the bottom may not stick. Remember, we talked about a viscous layer last quarter. Some of you weren't here, but so I'll describe it again. In open channel flow, there's where momentum transport is turbulent. We can describe the velocity profile in terms of a logarithmic velocity profile. Looks something like that. Z against the velocity. But near the bed, right at a smooth bed surface where the roughness isn't too great, the flow must be laminar, or at least at times be laminar. And the thickness of that laminar or viscous layer will grow until it becomes unstable, and then it collapses, wiped out. Then it grows again until it becomes unstable and collapses. That's a description of what happens at a point. It doesn't happen that way all over the surface, but at any one point it grows and falls. If you go to sleep on an airliner with your head next to the window, you can hear some noise of the wind going by. What you hear is that continuing collapse of the viscous layer. Or if you remember, the plane's going through air that was reasonably still compared to the velocity of the airplane as it moved along, so that somewhere just outside of that it's shedding eddy. This formation of a viscous layer, and we'll say that the average time of the I'll draw an enlarged view of it. The average velocity gradient in the viscous layer looks something like this. And we call this thickness here delta, and delta is equal to 11.6 nu over u star. Well, in our case here, we have a flux of particles coming down to the bed, but if that viscous layer is collapsing, then some of the particles that go to the bed will be taken back off again. So we need to account for that removal. And I proposed in those early studies that we describe that probability of the particle remaining as 1 minus the probability that it's removed. And I said, let's say that's proportional to the bed shear stress relative to some critical shear stress on the bed. Now, our flux removes the particles from the mixed layer above it. Above this, we need to account for that. So we can describe the change in concentration of suspended material as this divided by the depth. I'll call it d. And that's our dc dt. So the assumptions are that the rate of removal from suspension is equal to the flux downward to the bed times some probability term. A probability that it will stay, and that is determined by the depth. Now, I can write this in a different way. It might be a little more intuitively clear to you. This depth times dc dt is the change in mass of suspended particles per unit time. So this we can write as dm dt. And you'll see this written either way.
Mr. Krone,
Yes?
define your subscript
The tau, this is the shear stress on the bed, tau sub W. And tau subcritical is a critical shear stress above which particles don't. We need to put that in our equation too. So I'll write in here. Semicolon. Tau W less than tau critical. When the tau W equals tau critical is equal to 0, there's no deposition. Below that, there's a deposition rate. Now let's look back at that figure you just saw. The integrated form of this is log C over C0, C at time, for time t, divided by C at time 0 is equal to minus some constant, or I'll put it here, right?
Did I understand you correctly that D is the depth?
Erosion suspension.
No, D.
Is that tau C? In the last equation?
Critical. So this is what is shown by that figure that we just looked at least for the linear parts of that figure. Notice that below some concentration of about 300 milligrams per liter, they're all straight. Above that, there's some curvature. If they fit that relation, it means that W sub S must be true. I don't hear any agreement or disagreement. It must have been constant if it fits that relation. That, what's that?
I'm saying I'm just a paragraph behind.
Oh, no. Which means it must not have been here. And that is supported by the fact that some concentration, this relation doesn't, or there's some change up there. So at these low concentration, particle collisions must not have been a factor. In the system that I described with this recirculation, tension 12-inch pipe, the settling velocity was constant, or collisions were very infrequent. Let's look at now at what concentration. Look on page 43, and you'll see there that the all of this at C, right? The shear stress on the wall was constant, so as the fraction removed per unit time changed with bottom shear stress. Each one of those pluses represents another flume experiment, or one of the curves on that previous plot. And you'll see that the fraction fell off linearly with the with a shear stress, and that the intercept on the abscissa is about 0.6. So our tau critical here for that sediment is equal to 0.69 per square centimeter. That plot verifies this probability. It's an experimental demonstration that this is appropriate. Now, to tell you the truth, I didn't expect that to be a straight line when I did it. We did the experiment and it turned out that way. So this now is the case for infrequent collisions, where the particles don't collide very often, or where aggregation processes have already gone to some stage where the further collisions are very infrequent. Let's look at another extreme now, high concentrations of suspended particles, and you'll find them on page page 53 is a plot showing change in concentration as a function of time, and these are log-log scales now. And you'll notice that, and let me repeat, the experiment was proceeded in the same way. A high concentration of sediment, it's a different sediment this time. It's the material from Mare Island Strait. High concentration was suspended about 20 some grams per liter. At a high velocity, then the flow in the flume was reduced, so that the velocity was reduced to the point where sedimentation could occur. And then it was allowed to remain there. I think those are about 15, actually, I said 21 grams per liter. In that experiment, I think it was about 15 grams per liter, but a high concentration compared to the other one. And you can see that nothing happened for a long time. There are 4 curves on that. 2 of them represent gravimetric measurements and 2 of them optical density measurement. And we routinely did optical density measurements just as a backup for the
You're saying in figure 18, initially you had this velocity and then you reduced it, and this
Velocity
is
was
after the
0.4.
velocity reduction?
Yeah, after it was put in suspension at about 3 feet per second, then the velocity was reduced, and the concentration was measured. The upper curve, which is just straight across, refers to the upper abscissa as a way of stretching out the length of the plot. And you'll see it ranges from 0.01 to 10. Then the lower one begins at 1, and the lower curve begins at 1 and goes up to 400. You can see that some 10 hours or 8 or 10 hours passed before deposition became apparent. So the material just stayed in suspension during that time, and then it began to deposit. What was happening, we believe, is that aggregates were forming at that lower velocity that couldn't exist at the higher velocity that we used to suspend the material. The velocity was reduced, the velocity gradient structures to go. Aggregates had a higher area in the slurry with space that could now there's also that we had developed with a metal bed. The slurry may not have been adhered to the bed, and the structure was destroyed. Primarily, it was the velocity was near because there was no structure handy.
What's the kind of reduction you had here? It says this is velocity was
0.47
0.47 feet per second
from 3 feet per second. It's described in there, but the usual procedure was to suspend. It may have been suspended at 3 feet per second and reduced part way and nothing happened, so we reduced it further. I'm sure it's described in there in detail.
But it says, it's saying here that it takes,
It just kept no deposition or something like that. Oh, I should have was always measured at the end, so it was a completely mixed region that was completely mixed. Well, we have a situation where the structure, that is the formation of aggregates, rate was reduced, and then we had this velocity. And you can see that while there aren't many points there, the concentration was constant for a time, and less than an hour, or something on the order of an hour. Then it fell off at a slow rate like that we'd seen before. Then it fell off much more steeply. So we have a situation where the deposition regime changes with concentration. Now the velocities were kept constant throughout this period, so that the bed stress was nearly the same throughout the experiment. But we had a situation where nothing happened for a while, and that was, I explained earlier. Then hindered settling seemed to control the downward flux toward the bed. Then we had a situation where the concentration decreased rapidly. I'd like to describe these in terms of regimes.
Question?
Question?
Do you have a distribution along the flume of how the thickness of the particles that were deposited? It would seem like the pump would shear all the particles back to some consistent size, and then they'd come into the flume, and it would take a while before they'd aggregate to a size large enough to settle, so you'd go a little ways down the flume, and then you'd start getting a...
You'll find that in the... You'll find... in fact, it appears that the pump didn't break them up. Probably the greatest single factor, I'm sorry, I erased that. The greatest single factor was the shear stress on the return line pipe, on the walls of the pipe. And it was kept close to that on the bed, so that it was minimal. It appears that the aggregates weren't broken up in the pump. They were broken in the viscous layer next to the walls of the pipe and the viscous layer on the bed. Is all I'll explain in just a minute. Well, I'd like, in order to keep all this straight, I'd like to describe some regimes. And I'll bring you a paper that either the secretary will bring it down if the Xerox machine is fixed, or I'll bring it next time. One, let's call the first regime the one where the collisions are infrequent. And W sub S is constant. And 2, well, let's see, I'll put 3 and 4. The collisions are frequent. And W sub S varies. It's a function of concentration and velocity gradient. That is the frequency of collisions. Remember, the frequency goes up with the concentration squared and with the velocity gradient. Then the third one, it's the same as this, but settling velocity is hindered. And it's a function of these things. Then we can describe this one where, how shall I describe this? Frequent, certainly frequent. And no settling and it occurs at high C du dz. Now with this kind of a breakdown, we can look back at that curve. The upper one I mentioned was the slurry situation. When aggregates developed and we had hindered settling, then the long straight section there, which is regime 2, aggregates collided with each other very frequently in the viscous layer. The velocity gradient in the viscous layer is very high. It's the highest velocity gradient in the profile. So when the concentration is high, so there are a lot of aggregates to collide with each other, and the velocity gradient is high, then it continually breaks them up, and they mix upward into the waters above and re-aggregate and settle back down again. So we have a continuing breaking at this high concentration, continual breakdown of aggregates in the viscous layer, and re-aggregation in the layer up above. And on the scales that we're concerned about, when the velocity is reasonably constant, then you have a kind of a steady state or a near steady state relation.
You said
So our settling
velocity gradient is high, it's not highest,
highest in the viscous layer.
but that drawing doesn't illustrate that, does it?
Maybe I can improve on it. Can I just, I'll make two drawings. One is of something like this, and I'll just enlarge this area here now, right near the bed. That give you a little better. We have for this region here, we have U is equal to U star over K on constant, I'll call it A, U star Z over nu. So this is our logarithmic velocity profile. Down here we have U is proportional to Z. But the velocity gradient here is the greatest, and the reason for that is that the shear stress within the fluid increases with depth. And the greatest shear stress is right at the bed. And this is the elevation we call delta. Z equals delta at this point. See, we were talking about breakup of aggregates in the bed. So what our flux to the bed now is the flux of those broken up particles. Follow me. In addition to which, particles that contact the bed may or may not stick. Some of them are torn off by the velocity gradient. Recall that I said early when we were discussing aggregates that the aggregates in suspension are free to rotate. So the stresses on their surface, except when they collide with one another, are very much lower than the stress on the surface of the bed itself, where the velocity gradient applies shear to the fixed aggregate. So we have both of these processes taking place. That is, particles touching the bed and coming off, and particles settling to the bed. But now our settling velocity depends on that breakup and reaggregation of particles that takes place in the bed. On page page 56, there's another plot of the bed shear stress against the deposition rate. There's a YE there. And let me explain that. In the flume, going back here, we have the MDT. M is the mass of suspended particles per unit area of bed, right? Mass of suspended particles per unit area of bed. In the case of an open channel, that's simply the mass of particles above, say, a square centimeter of bed surface. In the case of the flume, we have a lot of water running around in the rest of it, in the recirculation system. So the change in mass of water per unit area of bed has to include the change in the mass in the return lines and pump as well. So that YE is the effective depth, or the effective depth of water, which is simply the volume of water in the flume divided by the area of the bed on which it deposits. In a channel, it would just be the depth. There. We'll notice that while there's more scatter than there was in the previous one, it still looks like a linear relationship supporting this description of the probability that the particle sticks to the bed. This is a different sediment, so the tau critical, the intercept with the abscissa, is different. This is about 0.8 of the dyne, I think, per square centimeter. But it's not that much different. So our picture here is that we have a settling velocity that's a function of concentration, which determines the frequency of collision in the bed and above, or near the bed and in the waters above, and the velocity gradients near the bed. It breaks up at high velocity gradient and reaggregates during lower velocity gradient. Then we already talked about the hindered settling and frequent no settling. Now if you'll notice back on that plot on page 52. Down at the lower end of that regime 2 curve, that steep fall-off curve, it appears that the concentration didn't change very much. Because it's a log-log plot, it's all collapsed there together, but you can see that the last 4 points really didn't change concentration very much. And that's well down in this 300 milligrams, about 300 milligrams per liter that we saw before the plot in the first plot that we looked at. I said that the reason that the particles didn't settle, or that they settled in a semi-logarithmic fashion at that low concentration, was that the settling velocity was constant and that aggregation processes, collision processes, were very, very slow. In order to demonstrate that, we put an industrial floor grid. You know, these grids that are made of ribbons of metal that are riveted together in a wavy pattern. I'm sure you've seen them. They're riveted strips of metal laid on edge like this, used for, or you see them around steam engines on ships and the like. We took a piece of that and placed it in the flow so that the water flowed through it in this direction to provide velocity gradients throughout the flow and to increase the apparent du dz. And that the result of that is shown by the dashed line, only optical density, going out the bottom of that plot and re-entering at the top and going on down. In just a few days, the water became crystal clear, showing that collisions were, in fact, the factor that determined the difference between regime 1 and regime 2. Well, this leaves us in somewhat of a dilemma, because most of our problems occur in regime 2, where the concentration's high and it causes deposition rates to be rapid, and so that dredging is required. Well, we can improve our situation somewhat by considering that first relation that I put on the board. I'll just write it this way. EM dt is minus W sub S C times 1 minus tau W over tau critical. But now we have W sub S varying in that region. Recall that I pointed out last hour that empirically we found that W sub S in this regime 2 is equal to some constant times the concentration of the 4/3 power after aggregation had been allowed to take place. That is, remember, with a plunger or by dipping a cylinder into a flume and letting the particles settle and measuring the median settling velocity. There were some that settled faster and some that settled slower, but the median was seemed to fit this quite well. So we can substitute for settling velocity in this relationship and have dm dt equals minus our constant times c to the 7/3 now, times 1 minus tau W over tau critical. So we have now our deposition rate is proportional to the concentration to something more than the square. Remember, this is empirical. You can rationalize it by talking about aggregates having a volume like the cube of their radius, proportional to the cube of their radius, and the settling velocity proportional to the square of the radius. And you can make arguments of that sort. But really, it's just an empirical relationship. But this then gives us something that if we assume the conditions under which this was made apply, it gives us a means of measuring the rate of loss as a function of the concentration here. Shrestha just finishing his thesis, and he took some data, some of these data and some other data, and investigated the possibility that you could write W sub S as a function of the velocity gradient, average velocity gradient throughout the flow. And he found that you could, and in that case you could write, I'd better say a little more about that. He said, let's suppose that W sub S is some function of the average velocity gradient, I'll call it G, and that's the concentration to some power, which is also a function of G, times 1 minus tau, or tau critical. The MDT, over here. Then he investigated the relation between observed settling velocities and concentration, and he came up that W sub S of G is equal to a constant, I'll call it A plus B times G, some linear function of G. But he came out with N of G is approximately equal to something greater than 2. 2 plus, very little bit, but not very much greater than 2. That's based on some unlimited amount of data. But it was interesting that this part would change linearly with the velocity gradient. Here.
What is G, please? What is G and...
G is the average velocity gradient in the flow, And that's equal, he chose that to be equal to the power dissipation rate per unit volume divided by the viscosity, the 1/2. This is Camp's. Camp's G. Calculated the power dissipation rate for the whole flow divided by the viscosity to the 1/2 power, and that you'll see that comes out with a dimension of per second. There's another way to use this, two other ways to use this relationship in deposition computations. One is to examine the hydrographic surveys of a harbor or some area of concern that you're trying to model, and determine the rate of deposition over a period of time, say 3 or 4 or 5 years time, typical. Sometimes as little as 1 year, but usually over several years. Then model that, and I'll explain how you do that. Just prepare a numerical model of that deposition rate using this relationship, and find the K, or the C rather, that provides that rate of deposition. Now it has a couple of advantages. One, of course, you're adjusting your model to an observation. You're not getting it independently, which would be better. But the advantage is that the concentrations in nature change over wide ranges continually. And it may be that most of the material occurs in a very short, most of the deposition occurs in a very, very short period of time when the concentrations are exceptionally high. The rest of the time is low. You can go out and spend literally tens of thousands of dollars measuring suspended solids concentrations at various times and miss those important times. So it's, in a way, it's useful because it gives you a concentration that represents the time. I've done this on a number of occasions, and the concentrations that you find are not very atypical. I mean, in a marsh, for example, in calculating the rate of rise of a marsh surface due to deposition, you can take core samples and date the different elevations from cesium-137 or lead-210 or some dating method, and determine the rate of deposition over time, and calculate using the model, find the concentration that gave you that same rate of deposition, and it turns out to be typical of what you find in a near-shore waters. So it seems to be reasonable. In harbors, enclosed harbors, you can take the hydrographic surveys and back calculate, and you come out with also very reasonable numbers. So I want to emphasize, this is strictly empirical. This has the rationale behind it that we discussed earlier, and this C to 7/3 just results from the fact that the flux includes C. That's one way to do it. Another way to do it is to simply go out and adjust your parameters until you get what you saw. We have two parameters. One is this tau critical, and the other is the W sub f. I have recommended to modelers that they go out and measure the settling velocities of particles near the bed to get their actual settling velocities. And you do that by lowering a tube horizontally. I'll draw you a picture of it. A plexiglass tube about this diameter and perhaps about that long, with fins on it, so that it will align itself with the flow, and supported by a harness, looking down on it from above. a harness that has bearings on either side. The harness comes up above and holds it this way so that it's horizontal. Then an arrangement whereby you can close the ends. The procedure is to lower to the depths of interest, and it lines itself up with the flow, and water containing suspended particles enter this tube. Then you close it with a spring arrangement and some stoppers. Usually use toilet cleaner plungers. With a bungee cord between them like this. And close both ends, then raise it to the surface while it's still horizontal. Then on the boat deck, turn it upright and measure the settling velocity of the particles in it. You can do that either by sampling, having sampling ports along its length and measuring the concentration, or one sampling port and measure the concentration as a function of time, both as functions of time. Then you can get the settling velocities and use that. That's had mixed success because, and this is called an Owen tube, after Michael Owen. He's a worker at the Wallingford Hydraulics Research Station in England. That's had mixed results, and the problem is finding time and a condition that's representative of what you're modeling. It's if you just go out and take samples somewhere, you'll find get all kinds of answers. But if you take a sample where the conditions have been uniform for a time, for example, in an open channel, you'll find that you get quite consistent results. Or if you go into in an area where the material is just moving into an enclosure, you get reasonably consistent results.
Question? Has anyone tried using a model like Cropper's model to find out when they would expect the critical times to be, and then gone out and tried to sample?
No, no. I say no. The Waterways Experiment Station has done a little of that. But the problem there is that the Waterways Experiment Station is a long ways from the area, and they don't get back and forth. It's a major effort for them to go to the Gulf, for example, or the Atlantic coast or something. So the measurements haven't been as carefully done as they might have been. Now I want to describe some circumstances in estuaries. I'll describe this at greater length in a future time, where making measurements of that sort make more sense. One is that in an estuary where the concentration is high, the tidal currents and the tidal currents are appreciable. You may have essentially a slurry, that is, material carried up into suspension, and if the concentration is very high, as in the Thames, for example, or the Gironde in France, or any number of estuaries where you have a large tidal range, concentration is high, you may have a slurry, and not much happens. That is, it's just transported back and forth with the tidal current, except near slack water. If I plot time against current, and we'll call this flood and this ebb. Flood means the water's coming toward the land from the ocean. Ebb means it's flowing from the land toward the ocean. The velocities might look something like this. And only during this period, this is zero, during this period near slack water, that is when the current reverses, are the conditions favorable to deposition. So during this period, you may have if the concentration is very high, you may have a slurry, and as you saw, it takes some time for a slurry to form an aggregates and settle. You may not really have very much deposition here. The concentration is really high. with the result that the material just moves back and forth. But if a portion of it turns off into an enclosed harbor where the velocities are low, then you can see that it carries the material in there and it will settle there, or in the lee of a wharf or some place where its velocities are low. Whereas out in the current, it's just carried back and forth. In regime 2, if you have a high concentration with hindered settling, you may get a layer on the bed that forms a sharp interface like we saw in the bottle the other day, and hindered settling is taking place down here. But before more than a portion of it can settle on the bed and consolidate, the velocity picks up again, and this is wiped off and carried back up into suspension. So that when you go out and take measurements of settling velocities using an Owen tube, it's important that you recognize the system that you're in and take suspended solids or settling velocity measurements at the appropriate place and the appropriate times. And it's a good idea to take them as a function of concentration, so you can see how they change with changing concentration and velocity gradients. Then you can empirically represent that in your model. Do you follow me? I'll bring you a paper next time that describes that a little better than I could do it verbally. Okay, so let me sum up right quick. We have the deposition depends on the aggregation of the material. It depends on the density of the material. It depends on the strength of the aggregates, that is, how susceptible they are to being broken up in the velocity gradient. And of course, it depends on the opportunities for collision, which depend on both the velocity gradient and the concentration. So concentration really becomes an important parameter. As you can see here, in this relation, it's something more than the square of the concentration affects it. So low concentrations behave vastly differently than high concentrations do in terms of deposition. My time's run out. Now, my homework is to find out whether that's 2 or 4, right? Was there anything else that I should do with regard to?
Why the velocities are so different for the flood and the ebb?
Oh, why did I show that? Well, it turns out that they are. And that comes in parts of estuaries. And that comes about because there's a net bias upstream on the bottom due to the more dense salt water intruding under the fresh water. So there's a net flow upstream. See, this is current here. So the area under this is the distance that it moves, right? In this case, upstream. In this case, downstream. So the distance that moved upstream here is greater than the distance downstream on this illustration. And that's typical of near bed velocities. I'll bring some actual examples and give you a slideshow. I think I've hit all the really important points. I'll bring you a paper next hour that reviews this material with a present perspective. That report that you're reading was a exploratory study, so it was done long ago. Since that time, there haven't been many studies done. I'll describe some others next hour. And it's a topic of continuing research. People are now in France and Holland and England are doing more work on deposition processes. So there's lots still to be learned. Well, I'll see you all on Thursday.
I used 4/3.
There's quite a bit on those midterms and finals that we haven't covered yet, so clearly you're not responsible for them. But it does give you a feeling for the type of questions that I ask. I can't guarantee that I'll ask exactly the same type of questions there, but definitely when you're trying to prepare for it, you don't need to cover points in the book that I didn't touch. Okay? In those reading assignments, some of them go into other material that you're not responsible for. The type of test that I tend to ask is evenly divided up between what I like to call show that is, make simple derivations, and I emphasis on simple. They're usually 1 or 2 liners at the most. Okay, and that's because you're limited to the amount of time that you have. Set up, but do not solve. Okay, there's a couple in there that you can see. I want you maybe set up a bunch of systems equations and the like, but I don't want you to go ahead and try to solve it because it's going to be too time consuming to possibly solve. And there'll be a couple plug and chug type problems. Once again, they tend to be on the straightforward and simple side. The one piece of advice I give to you on taking the test is if you're getting into a really involved calculation, and I haven't stated anywhere in there that it might be complicated. If you're getting into a really sophisticated problem where the equations are going everywhere, you may have done it wrong, okay? It's a very good chance because I try to make them very straightforward. Yes?
Do you have office hours on Monday?
I sure am. I'm going to be at the graduate students, the TAs, office hours. Can everybody make those 2 TAs office hours? There's one at, is it 10 to 11? And I believe 12.